These are two examples of peak models that have been constructed on spectra from PET. We've got an oxygen 1s and a carbon 1s. Both have a range of peaks, some of them primary peaks, others satellite peaks, but they indicate the chemistry for this material. We have, for example, oxygen and carbon in a double bond and a single bond with carbon, so we see within the oxygen two peaks, and that corresponds to the single bond and the double bond, whereas in the carbon 1s spectrum we see three peaks. These three peaks represent C double bonded to oxygen, the single bond to oxygen, and carbon that is part of a benzene ring. A typical peak model designed for these types of data would involve defining a set of components using line shapes and then introducing parameter constraints to limit the range for parameters such as the position, the full width half maximum, and the area for each one of these individual peaks. Now, the novel aspect of these two models is that these ratios of 1:1 for these oxygen peaks and the 1:1 for the relationship between these carbon bonded to oxygen peaks and 3:1 for the benzene ring to one of these two oxygen bonded peaks, this is all achieved by means of the line shape. Rather than using any parameter constraints, only the line shapes have been adjusted and fitted to these data to achieve a good chi-square and also the correct stoichiometry. We'll now look at why this LA line shape is capable of representing these data so well that we don't need parameter constraints. That is not to say that all peak models can be constructed without parameter constraints, but there are circumstances where the LA line shape favors a good outcome compared to other line shapes. If you consider how a hemispherical analyzer collects data, then this gives you the first indication of why the LA line shape works so well. So let's look at this in an ideal sense. So in a perfect world, we would have paraaxial electrons entering at a point source into the HSA, and these would contain a range of energies that when you split them in terms of energy, then you would have a Lorentzian-like line shape, and this is fairly typical of an s orbital. Spreading over the detector is this Lorentzian, and we have an aperture through which signal is allowed to pass and be detected and then passed on to the data system. And if this aperture was small enough, then we would see a point on this Lorentzian. But there's a finite size for this aperture, and so rather than actually seeing each point in this Lorentzian, what we have to do is integrate over the interval that represents the aperture through to the detector. So rather than seeing a pure Lorentzian form arriving at the data system, what we see is a transformed line shape that is no longer precisely the Lorentzian. So historically what has happened is that we've approximated this transformation from the Lorentzian to what we see in the data system using either a GL line shape, and this is a product form where we have the product of a Lorentzian. This is the form that we're expecting for an s orbital, so that's the shape here, and then we multiply by a Gaussian, and the Gaussian is attempting to model the way this Lorentzian has been transformed and arrives in the data system. So this is the product form, and the alternative to that is the SGL form, where again we have a Lorentzian, which is the expected input signal, and rather than modifying the Lorentzian directly, what we simply do is add a component of a Gaussian to this Lorentzian. This is the sum form of the GL line shape. So both of these are supposed to represent this altered shape that derives initially from a Lorentzian. This diagram is illustrating a snapshot of what happens in an HSA when a scanned spectrum is performed. So rather than having a static Lorentzian sitting on the detector, the energy is scanned and this peak moves across the detector. So for each energy you see a different area being calculated and reported to the data system. And this whole process is analogous to a mathematical treatment that is known as a convolution. You could see this as being a convolution of a top hat function with a Lorentzian. For an ideal instrument, a single detector with a single exit aperture will integrate the signal of this Lorentzian only over a limited interval. And this concept of integrating is the basis for a convolution. This is the convolution integral that is defined in terms of two functions, f and g. F will be the Lorentzian and g is a top hat function. And the convolution, in other words the signal at each energy x, is obtained by multiplying the Lorentzian with the top hat function for a given x value for the top hat function, and then integrating from minus infinity to plus infinity. So since this is a top hat function, it's only non-zero corresponding to the dimension of the slit, which has a corresponding width in terms of energy. So the product of this top hat function with the Lorentzian is simulating what the detector is doing, integrating over an interval of a Lorentzian. It's perhaps easier to look at this convolution integral graphically. Now the thing to look for is that at any given x value we're going to calculate an integral which represents an area that is formed from the product of the Lorentzian and a top hat function which is offset from the Lorentzian by this value of x. So here's the top hat function and here's the Lorentzian. That the difference between the position of the top hat function and the Lorentzian is 0, and so the area beneath the Lorentzian is the value that we're calculating for the line shape formed from a convolution, and the value for that area, scaled somewhat, has been depicted as a point. So let's see what happens if we move this top hat function around. Now the value for a convolution depends on the position of the top hat function. This is the g of x minus tau. So as I move the position for the top hat function, so the position for the point moves, and you can see as the overlap reduces, so the value of the integral reduces, and so the value of the point reduces. So we end up with a value over here where there's very little overlap, where it's a low value. So we perform a scan across a photoemission peak that was originally a Lorentzian. What we would actually see is the shape formed by this square top hat function. You can see that it's very flat across the top, so this is clearly not a Lorentzian peak, and we end up with a line shape that has been calculated from a convolution. Now if we alter this and make the shape of the response of the instrument or the detector not a top hat function but a Gaussian, then once again you can see that the convolution integral is formed and it provides a value for each of the positions for this Gaussian. So as I move the Gaussian, I get a different position within the convolution, I get a different energy, so I'm tracing out the shape of the line shape using this point by integrating the overlap of the Gaussian with the Lorentzian. And once again you can see that for a wide Gaussian, the shape that we will see from the detector and hence in the data system will be a Gaussian. On the other hand, if I make this a narrow Gaussian, then the intensity drops, so we're losing signal, sensitivity drops, and the result is that the dot now traces out something that looks far more Lorentzian. So a narrow slit or a narrow Gaussian response will produce a Lorentzian line shape, and a wide Gaussian or wide slit will produce more of a Gaussian-like shape. So this is the essential feature of the LA line shape. It's using a Lorentzian and it's being convoluted with a Gaussian. And by simulating what an instrument actually tries to do in terms of a convolution integral, we obtain a line shape that is more representative of the data that we actually record. When you form a line shape based on a Gaussian and a Lorentzian, then the line shape varies depending on the width of the Gaussian. So if we look at a set of line shapes that have been defined using a range of different widths, this third parameter here represents the width of the Gaussian. The same Lorentzian is used to construct these line shapes, so the only variation that you see here is the width of the Gaussian, and each of these line shapes have the same area and the same full width half maximum. And what we see as a result is that the wings of these peaks vary as we vary the width of the Gaussian, and the height of these peaks vary as we vary the width of the Gaussian. And that is because area is being moved from the wings into the peak maximum by increasing the Gaussian contribution. Using a Lorentzian convoluted with a Gaussian is a good starting point, but it does assume that you have perfect instrument. Real instruments tend to have geometric aberration. They also have other artifacts of the measurement process that cause peak shapes to differ from the ideal Lorentzian. So these PET spectra have been fitted using an LA line shape, but this time the Lorentzian part itself has been modified. So we're still convoluting with a Gaussian, but we can alter the wing to maximum relationship of the underlying line shape by making use of these first two parameters. In fact, here I've only got two parameters in total, and this means that the first parameter is repeated. The LA line shape will either have 3 parameters or 2 parameters. If you only use 2 parameters, then the first parameter is repeated, so the Lorentzian has been raised to a power 2 in this case. And by making use of these modifications to the underlying line shapes that we expect from the photoemission peaks, and then convoluting with the Gaussian representing a broadening due to the instrumental response, we end up with line shapes that in some instances can be used to create good peak models with the expected stoichiometry for standard materials such as this PET. PET demonstrated that the peak models for oxygen 1s and carbon 1s required line shapes that were different from a simple Lorentzian convoluted with a Gaussian. There may be a number of factors why that is the case. For example, the benzene ring was bonded with carbon atoms in 2 positions that were different from the other 4 positions, and so there could be some sort of asymmetry that is introduced by virtue of the chemistry. But one other way that you could introduce asymmetry would be related to the hemispherical analyzer and geometric aberration. If instead of having the perfect electrons coming in a paraaxial direction, we have a range of angles, then the trajectories within the hemispherical analyzer can produce a different position on the detector, which is equivalent to a different energy for the same energy electrons entering the analyzer. Hence, rather than having a pure Lorentzian shape as the input to the detector, what we have is something that might be more asymmetrical. Potential differences in the shape for the input signal can be accommodated by the LA line shape by virtue of the use of a convolution. That's to say that the first 2 parameters define the shape for the input signal, which is then convoluted with a Gaussian representing the response of the detector to this input signal. So if we look at the LA line shape as a convolution and look at the 2 response functions, we can see how the LA line shape accommodates the potential for asymmetry in the input signal. So this represents the response of the detector as the Gaussian form, and over here we have a Lorentzian, and it's a Lorentzian because we have the first two parameters set equal to unity and the third parameter set to 0. If, however, we set the second parameter to a value greater than unity, then we end up with an input signal that has asymmetry. And then if we then perform a convolution with a Gaussian of a given width, we have a line shape that is related to a Lorentzian that has been modified for asymmetry and then is then convoluted with a Gaussian to produce the final form that we fit to the data.